Hi, good evening, everyone. We are live once again for another workshop under TezAsia Hackathon. Tonight we have Anshu Jalan once again, smart contract engineer from TezSure, and we're going to the second part of building a dapp on Tezos and SmartPy. Yep, Anshu.
Thank you, Ivan. So, very good evening to everyone. So, yesterday we learned how about all the basics of SmartPy, and we wrote a very simple playground contract in the SmartPy IDE. And today we'll go ahead and create a proper smart contract, which will be a lottery smart contract. Now, before we get started, as usual, I would request you to go to this repository where I will be pasting links for several resources and also the contracts that we will be writing today and the slides that I will be presenting today. And Ivan, maybe you could put this in the chat. So as I said, we are making a lottery contract today, and it's a very basic contract. And how will it actually work is that we will have a total of 5 participants, and all of these participants can send one Tez each to the contract. And what they will get in exchange is basically, or they won't really get anything in exchange, but they are buying into the lottery game. And after 5 individuals are into the lottery game, there will be a random winner selected by the smart contract, and all the Tez, which will be 5 Tez in this case, will go to the randomly selected winner. So we also have some rules in this lottery game. The first rule, I've already mentioned that. So each ticket will cost 1 Tez, and a participant can buy as many tickets as they want. And since this is a random selection of winner, so if someone buys more tickets, then obviously they have a higher chances of winning, just like in a real world lottery game. And then we have a total of 5 tickets to be sold before deciding a winner. And finally, this is a very interesting thing. So the game is actually reset after the winner is chosen. So this contract is not a one-time use contract. Rather, we can have as many rounds of lottery as we want. So before we get onto developing the lottery contract, I want to explain a few design choices. Now, these design choices are some of these are related to SmartPy, some are related to Tezos, and some are general blockchain design choices. Now, these design choices often tend to frustrate developers when they are just starting out on their smart contract development journey. But as you keep using them, you eventually get a hang of them and you start respecting these design choices because they're really important choices. So let's get into them. And the first one is a Tezos specific design choice, and that is lists on Tezos do not have random access. And yes, you heard me right. So lists or arrays cannot be indexed on Tezos. So let's say we have a list here, and we can't use something like L of 3 if L is a list on Tezos. And the main reason for that is lists are implemented as linked lists on Tezos for memory efficiency. Because in the first case, you see, this is just a slotted array, right? But in the second case, we have a linked list where we have individual nodes with an item which has a value, and then each node is connected to the subsequent node. Now, why do we use linked lists? Well, let's say this is a slotted array, and we have a memory space in the RAM or the memory of the interpreter. And if the slot is only 5, if we only have 5 slots available, 5 consecutive slots, and we want to insert a 6th element, then in this case, the entire list has to be reallocated somewhere because we don't have another location there to insert an element. And this reallocation is really expensive. You don't really have to focus that much on why we do that. You can just Google it up, like why linked lists are more efficient implementation for general lists. But long story short, because of this, we cannot do random access. But another thing which we can do, because it's a linked list, is that we can traverse it. So something like sp.for item in L, which is just a standard a Python way of iterating across a list, that is possible on Tezos lists. So now the question would be, how do you actually simulate a random access list? Because if you're writing a proper logic in a smart contract, then at some point of time you would definitely need some kind of a random access list, right? So turns out we can do it in two ways. We can either use a map or we can use a big map. Now both of these ways are like really, really intuitive. In the first case, when I am using a map, what I'm doing here is I'm taking the key as a nat value. So nat is any number greater than or equal to 0. And the value could actually be anything. This value would essentially represent the type of the value within the list. So in this case, I've just chosen it to be nat for the sake of simplicity. So now whenever I want to insert an element or a value into this simulated list, what I do is I do L of sp.len L. Now what sp.len does is it's similar to the len in Python. And when we use len on a map, we end up getting the number of elements that are present in the mapping. So basically, if there are no elements in the map, the first value that sp.len of L will return is 0, right? So L of 0 becomes 5. So now you see this is just like random accessing or inserting into a list. The first value is 0, so that's like index 0. And then when we insert the first value, the length of the mapping becomes 1, or the number of items in the map is now 1. So sp.len will also be 1 for the next item that we insert. So this is exactly like a list where we are simulating it using a map where the keys represent the indices. And to get the value, it's once again just like a simple Python list. You do L of 4 in box brackets. Basically, you insert the index that you want. And then we have a big map representation. Now, the only difference between the map and big map representation is that if you have a very small number of values in the list, and ideally you even want to iterate over the list, then you should use map. Because as we learned yesterday, that big maps are not iterable, but maps are iterable. So if you want to iterate, you use a map. And if you have like a ton of values in the list, but you don't really want some kind of an iteration, but you just want pure random access, then you use a big map. But in big map, we don't get sp.len out of the box. Rather, we have to keep a state variable that tracks the current index. So in this case, let's say we have self.data.index, with the initial value of this variable would be 0. So the first value that we insert would be at 0th index, and then we increment it. So it's very intuitive to understand. At every value insertion, the index keeps getting incrementing, and eventually what we end up getting is a simulation of a random access list where you can access the values in just the standard format. Before going to the next topic, are there any questions in the chat box, Ivan? Ivan?
Someone from the chat asked, can we use a vector?
We don't have vectors, so like that's the whole point. We don't have vectors or any other kinds of arrays on Tezos. We have the normal list which I showed here, but this list does not have random access, so we have to simulate a list using map or big maps.
That's all from the chat for now.
Awesome. So next, local variables. Now this is a SmartPy specific design choice. So let's say in on the left hand side, I have a general Python program or a bunch of instructions in general Python. And how would you expect to sum up all the items in an array in Python? Well, you just have an initial variable where the value is 0. And I shouldn't have mentioned sp.for. It's just going to be for. And then you just iterate over all the items in some array called ARR, and you keep summing them up, right? And this works in Python, but it won't work in SmartPy. The reason for that is in SmartPy, because of the concept of meta programming that we discussed in yesterday's session, some ARR is not a variable, it's an alias. So when SmartPy program compiles down to other lower level code, or actually it's smart ML that it compiles down to, then some ARR is basically replaced with zero. So this becomes something like 0 plus equals items. That is what SmartPy tries to infer from it, because some ARR is an alias for zero. So that doesn't make sense, right? So this won't work in SmartPy. Rather, what you have to do is this. You have to explicitly mention that some ARR is a local variable and it needs to be changed sometime in the future. So in this case, the way we define local variable is using sp.local, and then we give some alias for the local variable. Ideally, we give the same alias that we provide here, that is the name of the variable. And finally, in the second value, we pass the initial value of the local variable. And finally, whenever you want to access or modify a local variable, you use the name and then you append a dot value field to actually use or modify the local variable. Now, today we won't be using the concept of local variables in a lottery contract, but this is something I just wanted to mention because you will be using local variables if you write a more complex contract in this hackathon. Now, this is actually a general design choice of most blockchains. And a few days ago, I also saw someone asking this question on the Discord channel, so that's why I chose to insert this slide. So on most blockchains, we don't have floating point types. So everything is in integers, or in Tezos, we have nat and integers. And the reason for not having floating points is that in a blockchain, we have several nodes that tend to work together, right? Now, when we have several nodes, there can be a precision issue in floating point numbers, because if some node rounds it up in a different way and some other node does it in some other way, then what we end up having is all the nodes have different sources of truth and they have different numbers essentially on them. So we avoid floating points altogether and we just have integers. But now the question is, how do we actually use floating point numbers? Because we still have to represent floating point or decimals in some way, right? So to do that, we use a different kind of a precision system. So let's say, just try to understand this. Okay, let's say if the precision is 4, then the number 1 will be represented as 1 with 4 zeros ahead of it. So we are scaling it up. So since we are scaling it up, if we want to represent 0.4 in a scaled up version, basically we'll have 4 followed by 3 zeros, right? We are scaling it up based on the precision value. And if we want to represent 0.002, then it's just going to be 20. Now it all depends on how many points of precision you want or how many digits of precision you want. For 6, it would be something like this. And for 8, it's going to be like this. Ideally, we choose a precision of 18 for something like tokens on the blockchain, because if you see, you might have to send something like 0.000, a few more zeros, and then 5 number of tokens. So for that, we really need really high precision. So most of the times you will see that if you're sending like 5 tokens to someone, the value that we enter is 5 followed by 18 zeros. That is because it's a precision of 18 or decimals of 18. So this is something you must note. Once again, we won't be using that in the lottery contract directly. I'll show a brief example of this in the lottery contract, but this is something that you will get when you get to tokens. That's where it's highly used. So let's get started with the lottery contract. Any questions out there, Ivan?
Someone from the chat asked, every time we're doing this for insertion in big map, it is a lengthy process, right? So why do we use this?
Wait, let me check the comments. Every time doing this, inserting in a back map is, well, it's not a lengthy process. It's O of 1. We are just inserting it into a big map. Just think about it. It's an O of 1 operation. It's not exactly a lengthy process. That's it, I guess, right? So yeah, let's go over and write the contract. So go to smartpy.io/IDE and click on create contract. And I'll give the name lottery. I will save it. And let's do some of the obvious stuff like importing SmartPy and writing a contract class. The constructor. I explained all of this in yesterday's workshop. So if you have any doubts, I would highly recommend you to refer to yesterday's session. So now we define the storage in the self.init function. So today, the first thing that we need in the storage is a set of players, right? Because as and when players are joining the lottery game, we need to keep a record of which players are in the game, right? So for that, ideally on other blockchains or other general programming languages, we could have used a list. But because of the efficiency mechanism on Tezos, in here, we will end up using a map. Now we can also use a big map, but since we just have 5 players and for such small values, we can just use a map instead of using a big map. So let's make a players field with the value as a map. Initially, it's an empty map. And the key, as we learned, would be of a NAT type. Now, you must make sure that the key is of NAT type, because if it's of integer, it won't really make sense because integers can be negative and array indices can't be negative. And then the value would be of type address. The value is of type address because it's the Tezos address of the user that is interacting and participating in the game, right? So we keep track of the user's address. Next, we need to assign a ticket cost for each lottery ticket. So we say ticket cost equals sp.tez1. As we decided in the rules, it's going to be 1 tez per ticket. Then we need to keep track of the number of tickets that are already sold or the tickets that are available or are yet to be sold. So for that, we will have another field called tickets available. And it's going to be a NAT type because it can't be less than 0. We can't have negative tickets, right? And the initial value is 5. And finally, there is a field where that is max number of tickets. So at max, how many tickets do we want there to be in the system? And that would once again be a NAT with the initial value of 5. Now, just one thing to clarify, there is also another concept of tickets on Tezos. Now, these tickets don't refer to those tickets. That is something that's a much more advanced concept. And today, the tickets that we're using here, these are just abstractions. It has nothing to do with that. Now, let's create the first entry point, which will be buy ticket. Now, using this entry point, a user will be able to buy a ticket. So how do we want the buy ticket entry point to look like? Well, the expected behavior would be just for confirmation, Brian, is the buy ticket slide visible? Because usually StreamYard stops the slides if I change the window.
It's currently it's visible. Yeah.
Yeah, it's the buy ticket entry point, right?
Yes. Yes.
Oh, okay, awesome. So the expected behavior of the buy ticket entry point is that a player sends 1 tez while calling the contract or calling the entry point, and then the player's address is recorded in the storage. Okay, because we need to keep a track of which player is actually participating. The number of tickets is reduced by 1. And finally, let's say if a player ends up sending more than 1 tez, right? Like by mistake, someone can actually send more than 1 tez, right? Then in this case, the any extra tez or extra remaining balance is then returned to the player. So in this case, what would the assertions or the verification checks that we need to do in the contract or in the entry point? The first one would be that tickets remaining must be greater than 0, right? If only if the tickets remaining is greater than 0 will you be able to buy a ticket, right? And at least one tez must be sent by the user, because the minimum cost of a ticket is one tez. So if a user sends less than one tez, it's not really valid, right? So let's create the buy ticket entry point. This won't have any parameters, so we'll jump straight to the assertions. Now the first assertion was tickets remaining must be greater than 0. So let's write that assertion. Self.data.tickets available greater than 0. Very simple. If this is not valid, then we throw the error, that is no tickets available. Now the second assertion is that at least one tez must be sent to the contract. Now if you recall yesterday's workshop, to access the amount of tez that is sent to an entry point, we use the global property or a call specific property, that is sp.amount. Now sp.amount must be greater than or equals to one tez. Now some of you might say that we can just go ahead and make it equals one tez and force the user to send one tez, but I just want to show you some extra steps. That's why I am doing greater than equal to one tez, because in that case I will be able to show you how you can return extra tez to the player. So just for the sake of that, I am doing greater than equals to one tez. But if you're writing a real world application, the more ideal thing would be to do equals. And the error, if less than one tez is sent, would be invalid amount. So that's all with the assertions. Now let's make the storage changes. The first storage change is that we need to insert the sender of the transaction, which is the player, into the player's mapping, or a simulated list. That is what the player's mapping is. So to do that, we do self.data.players. Now, just like we learned, to write the index for this, we can use sp.len. sp.len will give us the size or the number of items in the player's mapping. And this would be equal to the sp.sender. sp.sender records the address of the individual who sent the transaction. And then we need to reduce the number of available tickets. Tickets available. Okay, this should be tickets available equals self.data.tickets available -1. Now, if I leave it at this, I would get a very sweet error from SmartPy saying nat int mismatch. Why will I get that? Because like we learned yesterday, if you subtract a nat with a nat, what you get is an integer. And tickets available is of a nat type. So you can't put an integer in a nat type. So basically, we have to convert this type into nat. And how do we do that? We wrap it with an sp.nat, sp.asNat. And this will force this integer type to be of a nat type. Finally, we have to return the extra tez sent to the contract or the entry point back to the sender. So first we need to find what exactly is the extra amount. So for that, I'll set up an alias called extra amount. And this would be sp.amount minus the ticket cost. That is self.data.ticket cost. Now, there's one more thing. So I've explicitly mentioned sp.tez of 1 in here, but ideally it should be the ticket cost, because the ticket cost can, if you just change the ticket cost here, it won't change it here. So it would be nice if you can change it to self.data.ticket cost. Now, only if the extra amount, make sure you do sp.if. Just normal if is a Python if, which won't work in SmartPy. Only if the extra amount is greater than 0 tez will we end up returning the leftover amount back to the user. And to do that, what we do is sp.send. Sp.send is a way to return or send tez to some Tezos address. In the first parameter, we pass sp.sender, which is the address of the initiator. And in the second parameter, we pass the extra amount. So it's pretty simple. We are just checking what the leftover tez is, and then if it's greater than 0, we just end up sending it over to the user. So that's it. It's a very simple entry point. Any questions popping up in the chat, Ivan?
We have some questions from the chat.
Yeah.
First is if someone wants to buy more than one ticket, then what are they supposed to do?
Well, in this case, they have to call buy ticket multiple times because we are not checking whether someone has already bought the tickets, right? So they have to call buy ticket multiple times. Now, this is something which you can improve upon. So what you can do is instead of calling buy ticket multiple times, you can have a variable here as parameters like num of tickets. And then you can use that to actually buy multiple tickets in a single call. So that is the most ideal way of doing it. Just for simplicity, I haven't gone that way. But yeah, if you are building something for the hackathon and if you want, an improved version of this, you can, maybe go ahead with that. And in there you can buy multiple tickets with just a single call. This would be like a great thing to do as for homework.
Sure. I think this is a follow-up question, and I think you have to refer to the YouTube comments because they're asking why are we not writing? Then it's more about the code.
Mhm.
Can you go to YouTube and check it accordingly?
Why are we not writing? Well, we can actually write this, but we are not really changing the amount anywhere. It's a one-time alias. So if we use extra amount here, we are just checking if it's greater than 0, and we are using it. Because if we were doing something like extra amount equals some operation, like just any operation in here, then in this case we would need to make this a local variable. But in this case, we are just good to go with this, which wherein extra amount will be treated like an alias. Now, one thing, this is a bit advanced stuff. So as developers, when we actually make professional contracts, in that case, what we do is we wrap this entire thing in an sp.compute. Now, what sp.compute does is that it keeps extra amount on the stack, because you see, we are using extra amount twice. We are using it once here, and then we are using it once here, right? So we are using it twice. So in this case, if we don't use sp.compute, what happens is that this entire calculation of sp.amount minus the ticket cost is done twice, because this this is equivalent to this being taken and copy pasted twice. So basically what you see is just an alias. This entire calculation will be taken and copy pasted here by the compiler. But if you do sp.compute, then that copy paste does not happen. But since it's an advanced concept, I obviously didn't cover it. So this was just something extra. Anything else in the
There's one more question. Last one. Is verify an inbuilt function?
is verify an inward function? Inbuilt function. Yeah, it's an inbuilt function. But it's just on SmartPy. We don't have an equivalent sp.verify on Michelson. On Michelson, it's different.
That's all of the questions for now.
Awesome. So yeah, by ticket entry point, it was fairly simple, and you got to know some extra stuff about sp.compute. Now, The next thing would be the end game entry point. Now, in end game entry point, this would be a more complicated entry point, but still easy to understand. The first thing that we do in the end game entry point is that we generate a random winner. And how do we generate a random winner? Well, we generate a random number which equals to one of the map indices, right? You just pick an index, and against the index, you have a Tezos address, which will be the winner. Pretty simple. And then we send the reward to the winner. And finally, we reset the game. Resetting the game is easy. You just change the values of available tickets back to the maximum number of tickets, and you empty the player's mapping. And the assertion is very simple. We just need to be sure that all tickets have been sold, because until and unless all tickets are sold, we cannot end the game. Now, this is something which you can change if you're trying to make a more advanced lottery system. What you can do is you can have a start time and an end time. Okay. And it doesn't matter how many tickets are sold, but if the end is reached, then you just end up ending the game at once. So this is something which you can try out if you are making a better version of this lottery game. But as of now, let's start writing the end game entry point. Once again, no parameters here. Just one assertion, which would be self.data.tickets available must be 0. That is 5 tickets sold. Equals 0. And if all tickets are not yet sold, then we can send an error like game is still on. Now we have to generate a winning index. Now, how do we do this? Well, the way we do this is this. We take the block timestamp. The block timestamp is retrieved using sp.now, and that is the timestamp at which the block was created by the validator, or the baker as we call it on Tezos, and we modulo it with the max number of tickets. Now, this is very simple to understand. Since max tickets is 5, so what you will get eventually is a number between 0 and 4 included, right? So basically, you are getting an array index which you can use to pick a winner. Now, before going further, I would like to tell you that there is a problem with this method. It will work, but there is a problem that we will discuss. But first, let's go ahead and complete the entry point. So to generate a winning index, we write winner index equals sp.now modulo self.data.max tickets. Now there is a problem here too. sp.now is a timestamp, and we are doing some kind of a mathematical operation between a timestamp and a nat, right? This is not ideal. So what we do is we have to convert this into a nat2 so that this operation can go through. So to convert this into nat, just look carefully what I'm doing. The first thing that I do is I subtract a 0 timestamp from this. Now, when I do this operation, what I end up getting is an integer. Timestamp minus timestamp gives us an integer, and then we coerce it to a nat. So using this, we can convert a timestamp, or the timestamp that is sent during the transaction, to a nat. And then this operation will go through safely. Now we have a winner index. Now, using this winner index, we will get the winner's address. Get the address, we will do self.data.players, and we will use the winner index. And there you go. We have a winner index, and then using that, we pick up we pick a winner address from the player's mapping. Then the next step would be to reset the game. Or first, we need to send the rewards to the winner. And to send the reward to the winner, just like we did here, we use an sp.send. We do an sp.send. First, we will write the winner's address, which is stored in winner address. And finally, the amount of Tez. Now, to ideally, what we can do is just write sp.tez5, because we know that since the ticket cost is 5, then we will be having 5 Tez at the end of this. But instead, what you should do is you should send the entire balance of the contract out to the winner. Because if you don't send the entire balance of the contract, and sometimes if you end up changing the ticket cost, then let's say if the ticket cost is 2, then obviously sp.tez5 is incorrect. In this case, it would be 10. So what we do is we send the entire balance of the contract. And to find the current Tez balance of a contract, we use sp.balance. Now, once again, this is inbuilt. So if you use sp.balance, it basically gets replaced with the amount of Tez the contract is currently holding. Finally, we go ahead and reset the game. To reset the game, we have to do two things. The first is that we need to empty the player's mapping. And the second thing is that the tickets available needs to be set back to the max number of tickets. So self.data.players equals an empty map, and self.data.tickets available equals self.data.max tickets. It's really intuitive to understand. So what did we do here? First, we checked whether the game is over so that the number of tickets available is 0. Then we generated a winning index using the timestamp of the current block. And then we sent the reward that is collected in the contract to the winning address. And finally, we ended up resetting the game by basically resetting the fields that are in the storage. Any questions before we go further with the tests?
Someone from the chat asked, can same logic be used in LIGO?
Can same logic be used in LIGO? Yes, like why not? Tomorrow we have tomorrow we have a LIGO session where you will be building this same lottery contract in LIGO. So yeah, you will be getting a hands-on experience with LIGO too. Same contract.
The next question is, why can't we directly convert it to NAT?
Why can't we directly convert it to NAT? Because it's not available in SmartPy. That is the only answer I have. Because if you do something like this, sp.now as NAT, this won't work because right now it's not supported, or this is how it's designed. So you have to do something like sp.timestamp of 0. Now you might say that, okay, this is very inflexible. Why do we do this? But this is the beauty of strong typing. You can't write bad code with this kind of a strong typing. That's why on Tezos we haven't had such hacks like we have on other blockchains. Because of this extremely strong typing, it is very difficult to write bad code. So we don't have loopholes in a contract. But yes, because of this feature of Tezos, we need to do some extra stuff in the contracts. But at the end, it's worth it if you write huge contracts with very complex logic.
Another question is, can we trust the timestamp of the block for it to be random?
That is actually the problem, which I will be discussing in the next slide. That's why I gave a heads up. There's a problem with this method. So I'll come to it.
That's all of the questions.
That's all the questions. Okay. So yeah, I'll come to this question, this thing where there's a problem with this method later on. But for now, let's start writing some tests, because these are the only 2 entry points that we need for a very simple lottery game. So now let's start testing. Now, just as we learned yesterday, to write tests, we use the sp.add test decorator, and we give a name to the test. So in this case, we just have one test. So we give it the name main. Like that is my convention. I use the term main. A testing function. And the first thing we do is create a testing scenario, a SmartPy testing scenario. And then we need some test addresses or test accounts. Now here we have 5 players in total, so we will be needing quite a lot of accounts. So let's type fast. First we have Alice. Then we have Bob. I'll just copy paste. Then let's say John, Mike, and some other names, let's say Charles. Now, if I ever leave it at this is one mistake that I've made several times. This code will just not, it will work, but it won't work the way we want because there's a problem, and that is all of these are Alice. So basically, all these accounts are same because as we discussed yesterday, it's the string inside that is used to create this account. So we have to change it to some other string. And just for the sake of clarity, we could just make it Bob here. So the same name as the variable. Then John, Mike, and finally Charles. Then we define a contract instance. Let's call the instance lottery. And then remember, just once again, we discussed yesterday, you must put this lottery contract into the scenario, because if you don't do this, then the moment you call an entry point in the contract in the test, it will throw an error. Now let's start testing. First, we will test the buy ticket entry point. So let's call the buy ticket entry point using Alice's account. There are no parameters, but in the run function, we need to pass some things. And what do we need to pass? The first thing we need to pass is a value for amount, because there must be some Tez that needs to be sent to the contract, right? Or to the entry point. When you're doing it from front end, you actually use your wallet, like we discussed yesterday, to send the Tez. But in this case, we will just insert an amount field here and give it the value sp.tez1. And the next thing that we have to send is the sender value. So in this case, the sender would be Alice. Sender is Alice. Now, if I run this, the first thing that happens is the contract is compiled, and if I have any errors in the contract, then those errors will pop up. So let's click on run and see if there are any errors. I don't have any errors. That's rare. So here you can see that's the first transaction where Alice is buying a ticket. You can see the contract now has a balance of 1 Tez because Alice sent 1 Tez to the contract. And the max number of tickets is 5. But in the players mapping, we have Alice's address at key position 0. And the ticket cost is 1 Tez, and tickets available is 1 less than 5, that is 4 in this case. Now let's do this a few more times because we need to sell 5 tickets, right? So I'll just copy it a few more times. In the second case, it's Bob, then Mike, then John. And if I run it, now we have bought 4 tickets till now, so just 1 more ticket available. Now, ideally, when you are testing a contract, the good way to do it is that all the conditionals are executed. So right now, you see I am sending 1 Tez for every transaction, right? So this condition is never executed because sp.amount is 1, the ticket cost is 1, and extra amount is 0. So we never get to this conditional. So to get to that conditional, what we do is we send a 5th transaction with Charles. But this time, instead of sending one Tez, let's say we send four Tez. So Charles ended up sending four Tez instead of one. And if we run it now, in the final transaction, you see the balance of the contract became 8, because after the first four transactions of one Tez each, Charles ended up sending four Tez. So the balance became 8, but soon after, there was a transfer of three Tez back to Charles. And this is where the sp.send that we wrote in the conditional is being executed. So any extra Tez being sent to the contract is being returned back to the sender. Now, if you see the state of the storage, in players, we have all the players. Tickets available is 0. That means now we can go ahead and call the end game entry point. So to call the end game entry point, scenario plus equals lottery.endgame. Now the first thing that we do, or that's the only thing actually, we need to pass the now field. Now this now will actually be used here to calculate the winning index. So this is where the whole concept of reliability on now comes in. So if we pass now as 5, then in this case, sorry, what's the error? Is not a timestamp. sp.as9 timestamp is 0. Let me just check. Oh, sorry. So I have to do sp.timestamp, because now can't be an integer. It needs to be a timestamp. If I pass 5 as timestamp, then in this case, we see this is Alice's address, because Alice was at position 0. And if you pass 5, then 5 modulo 5 gives us 0, right? So the first or the 0th index is winning. Now, if this value is something like 3, then in this case, 3 modulo 5, the third index ends up winning. That is, yeah, this one. So now this is not ideal, because if we go back to the slides, the first issue is that on-chain randomness using sp.now can actually be exploited by a baker. Because let's say if I am a baker and I'm creating the block, then I know what the value of now is, right? Because I'm the one creating the block, so I know at what time I'm creating. So if I am a baker and I have a stake in this lottery, then I can just send the value of now that I want, right? So not ideal. It can be exploited by a baker. And another issue with this contract is that what if someone ends up sending funds directly to the contract? Okay, now this is related to one question that someone asked yesterday. So how are Tez sent directly to the contract handle on Tezos? In Solidity on Ethereum, we have something called fallback functions. So if you send Ethereum directly to a contract without calling a certain function, then there must be another function called a fallback function, like a default function that handles that sent amount. So in a similar way, we have something on Tezos which we need to use here, because if you're writing a proper application, you must ensure that there is no chance that someone ends up losing funds. So these are two things that we need to fix. The second one is very easy to fix. The first one is a bit tricky. So how do we do it? Well, when you're making a professional lottery contract, like that's just a term I'm using, in this case, the best way to generate a random number is doing it off chain, because there's literally nothing like on chain randomness. On chain randomness can be exploited, because even though we say things are unpredictable on the blockchain, it can be predicted by the person or the entity creating the block, because they do have some things under their control. So the only way to compute a proper random number is to compute it off chain. So basically, we end up having some operator. The technical term for this is an oracle system. And this operator works outside of the blockchain. So it computes a random number and it sends it to the smart contract. So you see, this is hidden from the bakers. The bakers really don't know which uh, which random number is coming in. They will know after they create the block, but they still don't have any control over the random number that comes in. So this is something which we will be doing in this contract. So to do that, what we do is we need an operator field in the storage, and this operator must have an address that will be calling the end game entry point. So when I do it, it becomes more clear. So just like yesterday when we were defining addresses in the storage, the way we did it was we used an sp.account and we passed in the admin literal and then appended dot address. So basically here this is an admin who will be an operator and control the end game entry point. Now, how will the end game entry point actually be controlled by this operator? The first thing we do is we provide an assertion, that is, the sender must be the operator, right? Because if anyone else is calling the entry point, that won't be valid here. So we say not authorized. And instead of generating a winning index, or instead of generating or taking a random number here for the winner index, what we do is we pass a random number as parameter. Now this random number is computed by the operator of chain. Now you might say that, well, what if the operator has stake in the game? Then the operator can just pass in a random number the operator wants, right? So ideally, the way this is done is using VRF, or verifiable random functions. This is an advanced level information. Today, we obviously won't be using that. But these random numbers can actually be verified to be actually random. So this is some advanced mathematical concept using which you can verify the randomness of a number being sent to the contract. Right now, if you want to explore VRFs, I have a link in the reading material. It's about Chainlink Oracle. So they have a VRF system, which should ideally be used if you're making a very complex contract. But in here, it's just a random number sent by the operator. So let's constrain the type of random number to that of a NAT, because that is what the mapping index is. And here, instead of doing all this complicated stuff, we remove this and we just use the random number to generate the winner. Now, if we want the tests to run properly, we need to make some changes. And the first change is that the sender in here must be the admin. Now we have to define an admin test account for that. And finally, we have to pass some random number here. Now, right now, it's obviously I am showing the random number to you all, but ideally it needs to be generated using some bot system. So let's say I pass 23, and if I run it, then 23 modulo 5 will be 3, so it's the third index winning. If I pass, let's say 25, 25 modulo 5 is 0, so it's Alice's index. As you can see, the 0th index winning the game. So yeah, I've been speaking for a while. There must be a lot of questions, Ivan.
Yep, some questions actually from the chat. The
Mm-hmm.
first one is why should full amount be sent instead of only one test? Will it give rise to locking of test issue?
Oh, wait, I have to see the question. Why should full amount be sent instead of only Tez? Will it give to rise to locking of Tez issue? I didn't understand why should full amount be sent, because if you want, like, if you're asking that instead of sending one Tez, why are we sending four Tez? Actually, I'm just doing that to show you this operation, because I could have very well done greater than, instead of greater than equal to, have just done equals equals. Now in this case, if I send anything greater than four Tez, anything greater than one Tez, then the operation will fail. So I'll show you. So in this case, you see this operation will fail. If I click on run, you see I'm getting invalid amount because it is always expecting me to send one tez. So I'll just make it one and it's all good, right? But I just wanted to show you how to return an extra balance. So that's why I did all this complex stuff. But otherwise, yeah, you can just go ahead and make it equal to one tez. Any
Right.
other questions?
Yep. The next one is why can't we use a random function?
There is no random function on SmartPy. So if you use the Python's random function, that won't work. That will work only during compile time, but when you run the contract on the blockchain, then there is no such thing as a random function on the blockchain. So unfortunately, and that's valid for all blockchains, not just Tezos.
And another question is how to send some random number.
Well, how to send is you send it from outside. So tomorrow I will not tomorrow, on Saturday I have, sorry.
Yep. Continue. Go ahead.
Yeah, so on Saturday, I have a Taquito workshop where I will be showing you how to interact with the contract from the front end. So you usually send random numbers from the front end, and it must be the operator address sending the random number. So on the front end, maybe if you have a JavaScript front end, then you generate a random number in JavaScript using JavaScript's random number generator. So like I said, this is not ideal. I'm just showing it for the sake of explanation of concepts. The more ideal stuff in professional setting is to use a chain link VRF, verifiable random functions. More questions?
I think that's all for now. Yeah.
That's it. Okay. So yeah, that's the lottery contract. And the next thing that we do is we deploy the contract. Now this is the fun part. We deploy the contract on a testnet. Now, just to note that we will be deploying the previous contract, the one which had on-chain randomness using the block time, just for the sake of simplicity, because in here we have to then set up custom front end for sending in the random number. So only for the sake of simplicity, we will be using the previous contract. And if you want the complete contract code, you can find it on this link. In this contract, I have also added some negative tests. So I'm actually testing the verify the assertions in the contract that I have on GitHub. So that is something extra which you can look into. But yeah, I'll just reset the changes that I made for the operator. I think that is it. Yeah, that's it. So now to deploy a contract, first you compile the contract, and then in SmartPy you go over to deploy Michelson contract. Now, obviously, this, like I said yesterday, SmartPy code is compiled down to Michelson code, and this Michelson is then deployed on to Tezos blockchain. So if you click on deploy Michelson code, you can actually see the generated Michelson. If I click on code here, you see this is the Michelson code that I showed you yesterday on the slides. Now you see this looks somewhat like assembly, but it's a proper high level language because we have actual types in here. And as you can see, it's quite huge. We have a lot of instructions. And this is the main reason that we use a high level language instead of directly writing in Michelson. These high level languages enable us to write logic properly. But yeah, one thing to note is that as you grow into a better Tezos developer, you will eventually get a hang of Michelson too. Right now, it's like, oh, it just looks like a bunch of instructions which goes over your head. But as you keep developing contracts, you would get a hang of Michelson, and you would eventually you'll start looking at Michelson code directly and make optimizations. That will take some time, but it's really fascinating to actually work with Michelson directly. But yeah, that's just some extra info. So to deploy the contract, after clicking on deploy Michelson contract, there's another button called deploy Michelson contract, and you click on that. And we get an origination page. Now to originate, first we need to choose a network on which we want to originate the contract. So in this case, we definitely don't want the mainnet because we are in the testing phase. So now Tezos, like I said, Tezos keeps upgrading, and we have had a lot of upgrades. And the last two upgrades were the Ithaca upgrade and Jakarta upgrade. So because of that, we have two test nets. On Ithaca net, we have the Ithaca protocol, and on Jakarta net, we have the Jakarta version. And right now there is a big change being made on Tezos. So maybe like when you are going through this hackathon, maybe after 10 or 20 days, you would realize that all of this is gone, and you just have mainnet and ghostnet in here. So ghostnet will actually be a long-term testnet which automatically upgrades, so we don't need a different testnet for each upgrade. Okay, so it's just going to be mainnet and ghostnet. So that is one thing which you might find later on SmartPy during this hackathon. So that's something you must remember. So for the time being, I'll just choose Jakarta Net. And now I have to use a wallet to actually sign a transaction. Once again, back to first workshop where we have to sign a transaction to send it onto the blockchain. And for that, I will be using Temple Wallet. So let's open up my wallet. I'm not sure whether there is another workshop to maybe like give you the basics of Temple Wallet, but I'll just show you how it works. So in here, what you can do is you can go to templewallet.com, and you can download the web extension. So you can download the web extension in Google Chrome, Opera, Firefox, whichever browser you are using. It has an extension for almost all the browsers except Safari. So you can download that, and then you can just follow some basic instructions. You can go ahead and check it out on YouTube. They have proper instructions on setting up the wallet. It's very simple. And after setting up the wallet, you can get some testing, some tests for testing. And to get some tests for testing it out, what you can do is you can refer to, or you can go to the Tezos faucet bot on Telegram. I have linked this up in the resources, I guess. So you can go to this faucet bot, and there are a bunch of instructions using which you can get some tests. So in here on Jakarta Net, I have 25 tests for testing and 60 tests in here. So this is something that you can manually do on your own. It's pretty easy. So yeah, to connect the wallet, I click on Temple, and then I choose Alice, and then I go ahead and estimate the cost for origination, and I click on deploy contract. I have to click on accept, click on sign. Now these are just basic stuff that you have to do. You don't really have to go too deep into what's happening behind the scenes. You will get to learn that when I give you the front end workshop, but right now, just to deploy the contract, you can just go ahead and follow the basic steps. And here the contract is deployed. Now to actually get a look into the deployed contract, what you can do is you can use a block explorer, just like in the first workshop I showed you tzkt. That's a block explorer. We have other block explorers like better called dev and tezblock on Tezos, which can also be used. So to where was it? Yeah, we can go to tzkt, which is jakartanet.tzkt.io. And if I paste this contract address, then yeah, this is my contract. If I go to entry points, I can see the two entry points, buy ticket and end game. If I go to storage, I can see max tickets, players, currently 0 items, the ticket cost. Now here you see, this is what I was talking about in the first workshop. The ticket cost is 1 Tez, but in here, in the contract, there is no such thing as Tez, it's all in new Tez. So 1 Tez equals 10 to the power of 6 new Tez. So that is what is being shown here in new Tez. And then we have our tickets available. Any questions before we proceed with the interaction?
There are no questions at the moment. Interesting.
No questions?
No questions.
Okay. So yeah, let's. So the next thing, and this is the last thing that we'll be doing, is that we will actually interact with this contract. So on Tezos, we have this really cool tool called Better Call Dev. Now on Better Call Dev, what you can do is you can call smart contract entry points and interact with a contract. So if I paste my contract address and choose the contract, then as you can see, just like tzkt, we can also see the contract operations here, the storage of the contract, and also the entry points in a contract. Now let's say if I want to buy a ticket, then I choose the buy ticket entry point in here, and I go ahead and click on execute. And then in here you have to choose the wallet option, click on Temple Wallet. Then you can choose any account that you want. Let's say I go with Alice. I click on connect. And surprisingly, it shows my transaction will fail for some reason I'm not aware of. Oh yeah, because I didn't choose the amount of this. So yeah, my transaction was about to fail, and the reason for that is I forgot to mention the amount of Tez I want to send. So this is just a classic failure of this sp.verify. If my amount is 0, then obviously I won't go through this verification statement, right? So in here I have to enter some amount. So I'll enter the exact amount, which is 1 Tez, or 1 followed by 6 zeros for mu Tez. Then I click execute once again. I confirm the transaction, and the transaction is sent to the blockchain. Now, if I just wait for a few seconds, I can see the transaction in here. And there you go. Here's a transaction where I'm calling the buy ticket entry point. And now if I go to storage, the tickets available is 4. And I have my address, that is Alice's address. As you can see, it's the same address in here that is inserted into the player's mapping. So using Better Call Dev, you can actually test out your contracts before you have a working front end. So this is an amazing tool. Usually what I do is I use Better Call Dev for interaction, and then I use tzkt for checking out how the storage and the operations look. So you can use a combination of both of these. So yeah, that is it for today. Any questions regarding the entire presentation, then please drop it in the comments. I will answer them.
I guess there are no questions. If you have
Eh,
any questions, you can always visit our Discord channel, and you can always ask our mentors from there, and they will address your questions. If there's nothing else, thank you so much, Hanshu, and I will
Yep.
see you again. I think Saturday or Sunday.
Yeah, Saturday.
Saturday, yeah, and we'll have another workshop for tomorrow. Yeah, have a good night. Thanks, everyone.
Awesome. Bye
Thanks.
bye.